A retriever trained on easy negatives looks good offline and fails on real queries. I'll show how to mine harder negatives from BM25 and dense candidates so hybrid retrieval learns from the mistakes that matter. This is the pattern you'll be able to implement by the end, which blends keyword and semantic signals to rank candidates and mine the most confusable negatives for training. I'm Professor Pi, teaching search and IR with simple Python. Hard negative mining matters because models learn from what they get wrong. If you train a retriever only on random negatives, it never sees realistic distractors. In practice, that means a model that ranks something plausible above the true result when users search. The remedy is deliberate. Find documents that are both lexically and semantically close to the query, but still wrong, and force the model to separate them. This improves ranking on real queries and reduces frustrating failures in production. At a high level, the idea is simple. Use a reliable lexical scorer to catch exact term hits. Use a semantic embedder to catch meaning matches even when words differ. Combine those two signals into a hybrid score, and then pick the top confusable, non-relevant documents as hard negatives. That forces the model to learn the difference between true relevance and close distractions. We will build a tiny toy flow that first scores documents with BM25, then embeds them with sentence transformers, fuses the signals into a hybrid score, picks a hard negative, and finally uses that pair for a margin loss update. The code is compact and mirrors what you would scale up. Now we will create a minimal BM25 baseline. This snippet builds a minimal BM25 search over a tiny list of texts and returns the top match. The variable docs holds short readable strings that mimic documents, and Q defines the query. BM25 OCopy creates a lexible scorer from tokenized documents, and getScores computes per document relevance for the query terms. The code then finds the maximum score to pick the index of the highest BM25 hit, and the final print reports the winning text and its score. If you tweak BM25 parameters K1 or B, you change how much term frequency or document length affect ranking. The printed top document shows the strongest exact term match, which gives us a lexical baseline to compare against semantic methods. Now we will compute semantic vectors and rank by meaning. This example uses sentence transformers to compute semantic similarity and produce a ranking. The object ST loads the all MiniLM L6 v2 model, and in code converts both corpus and query into vectors, with normalized embeddings set so cosine similarity behaves like a dot product. The arrays docE and QE hold document and query embeddings, and SIM computes their cosine scores through a matrix vector product. The index selected by NumPy argmax gives the best semantic match, and the output prints the top text and its cosine value. Using a larger model can capture subtler meaning, but increases CPU time and memory, so choose a model that balances nuance and latency for your use case. Next, we will fuse lexical and semantic scores into one hybrid ranking. This code fuses BM25 and sentence transformer signals into a single hybrid score. The array BM wraps the prior BM25 scores, and the code rescales them into a 0 to 1 range, so they are comparable to cosine similarities from SIM. A scalar weight A controls the trade-off between lexical and semantic evidence, and the hybrid score HN is a weighted sum for every document. The argmax of HN finds the best hybrid candidate, and the print shows the winning text and its fused score. If you increase A, you bias the system toward exact term precision from BM25. If you decrease A, you lean towards semantic generalization. The printed hybrid value typically sits between the pure BM25 and pure cosine numbers. Now, we will scan that hybrid ranking to pick a tough negative. This snippet mines a hard negative by scanning the hybrid ranking for a strong but non-relevant distractor. The variable pos ID marks the known positive document for the query. The list ranks orders documents by descending hybrid score using NumPy argsort on HN. And the code walks the list to skip the positive. It then selects the first candidate whose cosine similarity exceeds a threshold, THR, ensuring the negative is semantically close. Raising third demands tighter semantic proximity, which usually yields tougher negatives that expose real rank confusions. The printed negative and its hybrid score confirm we captured a plausible distractor that looks like relevance but is not the target. Next, we will convert that negative into a training signal. This example turns the mined hard negative into a training signal via a margin loss. The variables spos and sneg read the sentence transformer's cosine similarities for the positive and the negative. The margin M encodes how much higher the positive should score than the negative, and loss computes a hinge-style penalty when that margin is violated. If the positive already beats the negative by more than M, the loss is 0. Otherwise, the loss equals the shortfall. Increasing M toughens the objective and can slow convergence, but often yields stronger separation between true positives and close negatives. The printed loss shows how far the model is from meeting the target margin with the current embeddings. To map this toy flow into a real system, replace the in-memory cosine search with an ANN index for dense vectors and a proper inverted index for lexical search. Use batches of mined negatives per query and accumulate gradient steps in a training loop. Logging recall and a metric like NDCG on a held-out set will show whether the hard negatives actually improve ranking. Recap. Hard negative mining for hybrid retrieval combines lexical hits and semantic closeness to find realistic distractors. Use it when your retriever looks good on random negatives but fails on realistic queries. One caveat is that too strict or too many hard negatives can slow training or overfit to specific failure modes. Next step, tune the hybrid wait a while measuring NDCG so you find the best mix of BM25 precision and semantic generalization. If short, practical IR helps, subscribe and watch the IR videos.